So this video is going to explain the functions NGL lookAt and NGL perspective, and this demo here has a very simple camera which doesn't move based on NGL lookAt. It sets a viewing volume using NGL perspective, and then we do some modeling transformations just by creating a very simple model matrix which allows us to move the model around. So built into NGL we have a class called util, and util is just a whole series of free functions that are useful in computer graphics. And within that we have the function lookAt, which you see here. LookAt is based on either GLU lookAt, there's also a lookAt function in GLM, they're all very similar, and it can generate a mat4 based on three parameters that are passed in: the eye position, the center where we're looking at, and a vector to indicate which direction is up. And what we do is we use, as explained in the lectures, we calculate the n, the u and the v vectors, which are calculated from center minus I, and then we take the cross product for this vector n, which is looking into the screen, with our up vector, which will give us the vector v. We can then calculate the mutually orthogonal u vector, taking the cross product of v with n. We normalize those, and then we just populate our matrix. There's also a function called perspective. In fact, there's several versions of this with just different parameters in there. This again is based on either GLU perspective or GLM perspective. In this case, passing in a field of view, an aspect ratio, which is just the width and the height of the screen typically, a near and far clip plane, and we go through and we do the transformations of this to produce a matrix. So in the simple lookAt demo, I'm going to go through a little detail of some of the extra setup to help explain how all of the mouse movements and everything work. So we've got this structure called WinParams, which most of my NGL demos use. If we look at this, it's just things which are used to store X and Y rotation based on the mouse position, whether we're rotating, translating, the original X and Y position, and positions there, the width and the height of the screen. So this is basically populated when any of the key callbacks are called, which are in NGL scene mouse event, and it allows me to see if I've pressed a button, and I just calculate my difference in X and Y rotation each time and store it in the structure. So depending on left button, right button, we'll change things there. We've also got the wheel, which we use as the zoom. So available to us is basically how our mouse, when we click, is positioned relative to the screen coordinates, and I'll use these later. So in NGL scene here, I have a mat4 called view and a mat4 called projection, and what these are going to be used for is to set my view matrix, my projection matrix. We will pass this into the shader, and this will be used to calculate our view projection matrix. We will then also calculate this nMouse global TX, which is basically my modeling transformation for the current thing. So we'll combine together model, view and project to create one single matrix which will transform all of our points. So in this case, I'm only calculating the view and project once. So to create a lookAt matrix, we create our from. So in this case, it's just 222. Where we're looking to, the center of the screen 0, and look in my world is set to up. We pass these into NGL lookup, and that will return back a matrix, which is our view matrix. For my projection, I'm setting in the field of view, width over height is my aspect ratio, and I'm setting some arbitrary near and far clip planes. These are actually quite large at the moment. We can customize these to give us better precision. My mouse rotation is being calculated here. So I've got a NGL transformation. Again, that's explained in the lectures. All this does is allows us to combine together different transformations, and in fact in this demo that's not actually being used at all, so I think that's just legacy. Yeah, so in this case I'm actually just doing it all with matrices. So I've got a mat4 called rotx, mat4 called rotY. I'm calling the methods within the mat4 class to set these current matrices based on the rotation values from my window. So I've got an X rotation and a Y rotation matrix, and I say my mouse global transform equals rotation Y times rotation X. The model position here is my X, Y, and Z position from moving the model around with the left mouse button and the right mouse button and the wheel. So that allows me, I could create another matrix and multiply it, but it's easier to just set those directly because they don't affect the other elements of the matrix. And the key now is every frame that I draw, I load to my shader this matrix which corresponds to a model view project matrix. So I'm combining this together because my shader needs other matrices. So I say here my model matrix is my global mouse transform. My model view, which I'm using for transforming into I coordinates for my diffuse lighting calculation, are model times view, and my model view project equals model view times projection. And at the moment this is using the NGL built-in shader, which is NGL diffuse, and NGL diffuse is a very, very basic shader for diffuse lighting. We can open it up here, and you'll see here that my diffuse shader has an input of type vec3. So this is the generic vertex attributes coming in. So my input in this case is a vec3. So I construct a vec4 here so that I say this is a point, and every vertex that comes in is multiplied by model view project and passed to gel position, which later goes on to rasterization. You will also see here that my other elements, in fact, I am only using MVP and normal matrix in this shader as well, so my calculations that are loaded in there don't need to be there either. So in fact, it's only MVP that's going through. I could simplify this a little bit. I think that's just been kept for legacy. So you can see that my code rotates, the model position, we can move it around. It's a very, very simple way of having a nice fixed camera to move around. Very few calculations need to be done.